Okay, now let's do some examples of this quadratic curve. Okay, let's do some examples. Okay, x squared equals y plus 1. What this curve is? Well, you see, it's x squared and y is degree 1. So this is a parabola. This is a parabola. So sometimes the parabola is not centered at origin. So it is possibly you get some translation. Parabola. Okay. What is its vertices and the foci? What is its focus? So we have x squared is 4py. In this case, the focus, so it will be looks like this. P is positive here. So its focus is here is P. This is the directrix is also negative P. Okay, negative P. Okay, so here this we get. You can write in this manner. This is, so what is P? So P you compare 4py. For P you get this is equal to 1. So P is a quarter. Okay, P is a quarter. Okay, so it's translated. So this translated upward. So when y is negative 1, then you get a 0. So it's actually translated downward by 1 unit. Translated downward by 1 unit. This is negative 1. So it's directrix. So P is a quarter. So if you translate downward by 1, then this the foci, the focus will be translated a quarter downward by 1. So you get a negative 3/4. Okay, y coordinate, x coordinate is of course 0. Okay, then the directrix is at this is negative a quarter. Okay, negative P downward, translate downward by 1 unit. So the directrix will be the line y equals negative a quarter, translate downward by 1. So it's negative 5/4. Okay. This example. X squared equals 4y minus 2y squared. Okay, first of all, you write it as this manner: x squared plus 2y squared minus 4y is 0. And then you complete the square. Complete the square. So the x squared plus this is twice. This is y minus 1 squared minus 1 equal to 0. So this you get. This is x squared plus 2y minus 1 squared minus 2 is 0. So this you get divided by 2. So x squared divided by 2 plus y minus 1 squared equals 1. Okay, so you see this is of the type x squared over a squared plus y squared over b squared equals 1. In this case, we get an ellipse. Okay, we get an ellipse. But here, this ellipse is not centered at origin. So it's a center at y is 1. Y is 1. Okay, so y centered at 1. Okay. Now if it's centered at the origin, it looks like this. It looks like this. Okay, so the x direction, a squared here. If you compare, a squared is 2, so a is root 2. So root 2 is around 1.5, 1.4. Okay, so it's 2, 1, 1, 2. Now the center is the b squared is 1. b should be 1. So is this part? So a rough graph of, or if it or center at origin O, this is -1, this is 1, this is root 2, this is a negative root 2. And then we translate the thing upward by 1 unit. Translate it by upward by 1 unit. Then it will be, let me plot. Translate this thing upward by, so it will be, looks like slightly bigger, because in theory we should use 1 root 2. Remember, root 2 is around 1.5. Okay, this is more or less work. This more or less work. Okay, so this point should be root 2. And this point is assumed to be negative root 2. Okay, this is 0. This is 2. This is 2. Then we are done. For this. So it's translated. It's not necessary at the origin O. Example. Okay, for this example, we will try to move terms so that so this we get the left side. This is the y plus 1 squared minus 1. Public square from here. Then subtract x squared. So move 1 to the other side. Subtract 3 is 0. So this is actually what is y plus 1 squared minus 4x squared is 4. Divided by 4, then you get y plus 1 squared over 4 minus x squared is 1. So this will be this looks like this: y squared a squared minus x squared over b squared is 1. So this is hyperbola. This is the hyperbola. The hyperbola centered at not 0. Okay, so this thing looks like this. So with asymptotes, so it will be looks like this. Two branches. Okay, 2 branches. This part is a, this part is a. So if you compare, a squared is 4, so we get a is 2. B squared is 1, so we get b is 1. Now the asymptotes is, you said y squared, then you get a y squared, a squared minus x squared over b squared is 0. Then you get y over a equal to plus minus x over b. So a is 2. So this the y is 2x plus minus. Okay. Now here the only difference is we need to translate the thing. Translate the thing upward and downward by 1 unit. Translate downward by 1 unit. Okay, so this will be y equals negative 2x. This 1, this point is 2. Okay, so if it was centered at a 0, centered at the origin O, then it will look like this. A is 2, b is 1. So this is the box. It looks like this. Okay, asymptotes. The other part. Okay, now we translate the thing. We translate the thing downward by 1. We translate the thing downward by 1. Then you can, of course, you can translate the graph, or you can translate the coordinate. You translate the coordinate. The easier way is translate. This is a coordinate. Translate this coordinate upward by 1. So this will be the thing. This will be 0. Okay, translate the upward of the coordinate. Then you get this curve. Okay. This is -1, -2, -3. This will be 1. Okay. Then we're done for this curve. Now, how do we find its two foci? How do we find its foci? What is C? Remember, C squared is A squared plus B squared. C squared is A squared plus B squared in the case of hyperbola. Then A squared is 4, C squared, B squared is 1. So C is 5, root 5. Now, root 5, we should subtract it by 1. So this actually, the foci will be here, root 5 minus 1. Root 5 minus 1. Okay, another one is root 5 minus 1. Negative root 5. This part, the foci is negative root 5 minus 1. Translate downward by 1. Okay. Okay, so this is the examples of the case when the conic curves is not centered at the origin O. We can get equations that it via translation. Okay, up or down. Now we start to study another property of this conic curves, i.e., how light is reflected on this surface on a conic curve. Okay. Question. We first start with easier. How light is reflected? How light is reflected on conic curves? Now we start with laws of reflection. Laws of reflections. Okay, this is not part of physics. So suppose we have a surface. Okay, surface. Now light is reflected on the surface. Suppose this is okay. Light. We have a ray. Okay. So it's hard to plot use surface plane. So this ray is called incident ray. Okay, incident ray. Incident ray. Okay, so it's the surface. Then the how light is reflected. Okay, then we have this dotted line is called the normal line. So this is normal line. And then we have θ1 equal to θ2. θ1 equal to θ2. θ1. So the law of reflection says θ1 equal to θ2, where θ1 is called angle of incidence. So this is angle of incidence. And θ2 is called angle of reflection. angle of reflection. Okay, so this is the law of reflection. Okay, now we will use this law of reflection to study how light is reflected on the Conic curve. Okay, we start with so theta1 equal to theta2. Also, you also get alpha equal to beta, because you know the normal line is perpendicular to the surface. Okay. So alpha beta is the supplement. So we can get alpha equal to beta. Also, we can also get alpha equal to beta. So the equivalent to the law of reflection. Okay, now let's study how light is reflected on a parabola. Okay, suppose we are given a parabola. How light reflected on a parabola curve. Parabola. Okay, suppose we are given equation y squared is 4px. P is positive. Then we plot its graph. It looks like this. Okay, this is x-axis, and we have the directrix, and we have the focus, and then quadratic curve. So any point quadratic curve. Okay. So any point P on this parabola, then we have F. And this line directrix is called is the line L. Okay. So we have PF equal to PR. PR is perpendicular to L. So here we have PR is perpendicular to L. And PR equal to PF. By the definition of a parabola. Okay, by the definition of parabola. Now we will show that. We want to know how light is reflected. Now we will show how light is reflected. Now suppose we put a light source at F. Suppose there exists a light source at F. Okay, and then we want to study how light is reflected. So suppose, okay, the light is at F, the light source is at F. Then we have a beam of ray FP. And then we want to know how this P at light is reflected at P. So for a curve, and then locally we use tangent line to approximate it. Okay, use tangent line so that we get a flat surface. Okay, so we get a flat surface. Okay. Okay, now we assume that okay, suppose we are given the point P. Okay, we are given the point P. Now let this line be S. Let PS be the angle bisector of the angle RPF. Now suppose claim PS is exactly the tangent line, to the parabola at P, tangent at P. Okay. Now assume this claim for now. We will later show this. So this claim. Assume this claim for now. Then you see what happens. How light is reflected. So suppose we have PF. How light is reflected. Now, so you get this angle alpha. Then you get this angle beta. Then you get this angle gamma. Okay. So you see alpha. Look at this picture. Look at the picture. So what relation do we have? Then alpha equal to gamma, because definition of bisector. So definition of bisector, then alpha equal to beta. Now, alpha equal to beta. This is reflection law of reflection. Now, you see, then we get gamma equal to angle gamma equal to alpha, beta. Then this means the output, let's say PQ. This means PQ and PR, they are collinear. Okay, PQ. So this means alpha equal to beta, gamma equal to R beta. This implies PQR are collinear. i.e. PQ, the line PQ is horizontal, because here PR is perpendicular to the vertical thing. So this means PQ is horizontal. Okay, so this is actually a very important property for this problem. Okay, so this means PQ are horizontal. Now you see this point P is arbitrary. Then you see a really nice property of this parabola is if we put a light source at the focus of this thing, of this parabola, then the output light is actually parallel light. Now parallel light has really nice properties. It can go really long. Okay, use this property. Actually, people design the headlight of auto. Okay, now let's explain. Let me explain why this bisector is actually the tangent line. Any question about this? This idea? Is anyone has any question about this? Alpha equal to gamma, alpha equal to beta, alpha equal to gamma equal to beta. And then this implies PQR are collinear. This implies PQ is horizontal. Any questions? Okay, so next step. Now we show our claim. Our claim. i.e. The bisector is exactly the tangent line. The bisector should be exactly the tangent line. Exactly the tangent line. Tangent line at P. Okay. Assume not. We use contradiction. We use proof by contradiction. Assume not, then if it's not tangent, then it should intersect at the 2 points. Now tangent line intersect this parabola at 1 point with multiplicity 2. Now if you plot the points that has equal distance to the line and the curve, then you get the thing. Okay, suppose we have this this curve, and we have this point P. This is F. This is our R here. Now we use geometry. Now assume that the tangent line at intersect the assume we have some point Q. Here, of course, Q does not exist. Assume by contradiction. Assume that the bisector intersects the parabola at another point Q. Now what do we have? Now if we connect QF, and then we get QF equal to QR. QF equal to, according to the definition of the parabola, let's use this BT. Then we have, by the definition, then we have QT equal to QF. Okay. All right. Now let's connect QR. So T is different. T is different from R because Q is different from P. Okay. So let's connect QR. Now, by geometry, bisector, then we have angle RPS. What is P? P is this point P. Okay. RPS equal to angle FPS. Bisector. Definition of bisector. So bisector. This is because bisector. So now if we use 100 subtract that thing, then we get QPR equal to QPF. Okay. Then we have, you see, PR equal to PF. And we also have PQ equal to PQ. Okay, look at that. And also we have PQ equal to PQ. Look at the triangle, the two triangles, PQ equal to PQ. Then we have triangle QPR is congruent to a triangle QPF. By what theorem? By what theorem? Side angle, side angle side. By side angle side, SES. Okay, then we can conclude. Then we can conclude the corresponding edge, corresponding side. Then we get QF equal to QR. Okay, now remember QF equal to QT. QR equal to, remember QF equal to QT. QT. So this means QT equal to QR. Okay, you see. Okay, let me what happens if QT equal to QR? You see on this picture, what happens? QT equal QR. What is QT? What is QR? Anyone see why? What happens if QT equal to QR? Can we have QT equal to QR? Why? What happens if QT equal to QR? Can QT equal to QR or not? From geometry. Now you see, QTR is right triangle, and QR is a hypotenuse. Okay, PQR is hypotenuse. So which the hypotenuse is longer than any other sides in a right triangle. So this means this is not possible. Okay, so this is, so here we know QR is hypotenuse. Hypotenuse of the right triangle. Right triangle QTR. So which means QR not equal to QT. However, we assume by contradiction, if the bisector intersect at 2 points, then we get a contradiction. So this is a contradiction. The contradiction shows that it's not possible that Q is another point different than P. This shows that another point is not possible. The bisector intersect the parabola at exactly 1 point. Exactly 1 point. I.e., this is possible only when it is tangent line. The bisector is exactly the tangent line. 另外档 ，OK， 另外档 ，OK。Then we know if we put a light source, a point light source at the focus of this parabola, then when light reflected, then the light will be parallel. Then the light will be parallel. Okay, light will be parallel. So you get a parallel light in this manner. Then people design the auto light. Use a rotation. You just rotate the parabola along with respect to the x-axis for this example. Okay. So you get a good parallel light. All right. So this explains how light reflected on this problem. Now let's you may ask, okay, what happens if we have an ellipse? Question. How light is reflected by an ellipse? Okay. Now suppose we have an ellipse. Let's suppose we have an ellipse. Now let me insert an ellipse. Okay, suppose we have an ellipse. Okay, ellipse. It has two foci, F1, F2. All right. Maybe it's bigger here. Put it here. Okay. Now we want to know how light is reflected. Suppose we put a light source at suppose that there exists. Suppose that there exists a light source at F1. So suppose we have a point P. Now suppose we have a ray P F1P. And then we want to know how light reflected. Let me first mention the conclusion. The conclusion is for any ray F1P, whatever point P on this ellipse, then the reflected light always pass through the point F2. Conclusion. Then for any point P on the ellipse, the reflected light passes through so F1 is one of the one focus, pass through another, the other focus. The other focus F2. The other focus F2. So this is conclusion. So this is remarkable property. Now actually we use the same idea. Now prove this property. Now we want to prove this property. What we do is we assume we first find the tangent line. Okay, so we find the bisector. So this problem is a little tricky. This problem is a little tricky. So what we do is we first find, okay, extend. So what we do is we extend F1P to F2 prime such that PF2 prime equal to PF2. Okay, so what we do is we extend here F2 prime. Okay, then we do the bisector. Let L be the bisector of the angle F2 prime PF2. Okay, what we do here is we use this. Okay, bisector. Now, what we have is, you see, this is let this be alpha, this be beta, this be gamma. Then we have, okay, look at this picture. Then what do we have? By definition of a bisector, what do we have about the relation between alpha and beta? So this is L. Okay, then we conclude alpha equal to beta. Okay, alpha equal to beta. This is because definition of a bisector. Now, if L is tangent line, then the law of reflection says alpha equal to gamma. Okay, law of reflection. Okay, now if L is exactly the tangent line, this is exactly how light is reflected. Okay, this is exactly how light is reflected. So it is, so if we claim so here the only thing that we need to show is that line L, the bisector, is the tangent line. It suffices to show that L is the bisector. The bisector is exactly the tangent line. The tangent line. To the ellipse at P. Okay, so we need to show that L is a tangent line. Okay. Now we use the idea similar to what we did last time. So now we show that L is exactly the tangent line. Okay, now we use contradiction. Suppose we have another point Q. Okay, let me plot another picture again. So that you can okay, let me plot another ellipse. Oh, this one is bad. Let's delete it. Okay, this one is okay. Okay, suppose we have another, suppose we have this is F1, F2. So we have point P. Okay, so we have a line P. Okay, so we have another PF2. Okay, P. Now suppose by contradiction it intersect at a Q, L. Let's use S. Okay. Suppose by contradiction, although I'm plotting in this manner, here this Q doesn't intersect, so Q doesn't exist. Suppose by contradiction, suppose the PS intersects the ellipse at another point Q. Then what do we have? Then use the property of the ellipse. Then QF1 plus QF2. Let's just erase this magnitude notation. That's QF1 plus QF2 is equal to 2A. 2A is fixed. A is fixed. A is the, so 2A is the length of the longer axis. Okay. Okay. Now we do something. Remember, PS is bisector. Bisector of the angle of angle F2 P F2. Okay. So if we have a triangle, we have some geometric condition. So let's connect P QF1. So let's see some relation. Okay, what relation do we have? What relation do we have? So we have congruent triangles. So what is triangles are congruent? Can you see? What triangles are congruent? Can anyone find some congruent triangles? Can anyone find some congruent triangles? Can anyone find congruent triangles? What triangles are congruent? Remember, we by our choice, PF2 prime equal to PF2. By our choice, by construction. Okay. PQ equal to PQ. You know. PQ equal to PQ. This is trivial. Now, how about the angle, the other angle? How do we use the bisector? Bisector property. How do we use bisector property? Anyone know? The bisector property. The bisector tells us, so PS is bisector tells us angle F2 prime PQ equal is congruent to F2, sorry, is F2 PQ. Bisector. Okay, this is because bisector. Then we can conclude by, you see, we have Look at this carefully. These two triangles. These two triangles. Let me. Okay, look at this triangle. PQF2 and PQF2 prime. They are congruent. They are congruent because this angle is congruent to this angle by definition of bisector. Then the complement will be also congruent. So we have this side equals this side, an angle equal to this angle, and they share a common edge, common side. So by SAS, the two triangles are congruent. Okay, the two triangles are congruent. So we can conclude. Triangle PQF2 prime is congruent to triangle PQF2. Okay, so we can conclude. QF2 is congruent to QF2 prime. Okay, so okay, this is exactly what we want. Now remember F1 plus QF2. This is 2A. Now QF1 is just QF1. Now QF2 is QF2 prime. So this replace QF2 by QF2 prime. So you get a QF1 plus QF2 prime is 2A. Now 2A is also equal to, remember, PF1 plus PF2. This is also equal to PF1 plus PF2 prime. Okay, so this is a PF2. Sorry. It's no. PF1 plus PF2. This is equal to F prime, F1, F2 prime. So what we finally get is this relation. Q F1 plus Q F2 prime equal to F1 F2 prime. Is this possible in a triangle? Is this possible in a triangle? Is this possible in a triangle? This is not possible because the triangle inequality. The shortest distance between 2 points is a straight line. Okay, so here the shortest distance from F1 to F2 is the straight line between them. So any other point is longer. So we get triangle inequality. So line segment QF. So we get line segment QF1 plus the line segment QF2 prime. So the bigger line F1 F2 prime. Triangle inequality. The two sides is longer than the sum of two sides is longer than the third side. Okay, it's longer than the third side in a triangle. So here we get a contradiction. So from on one side we get this thing equal, on the other hand we get this thing is bigger. So we get a contradiction. Okay, so we get a contradiction. Which contradicts the triangle inequality. You see, we use nothing fancy about the property of this ellipse. We only use the definition, the basic property. Okay, now you see this thing, how light reflected on this curve is exactly related with the definition of this ellipse. Okay, now this actually is remarkable. Okay, it's a remarkable property. Okay, so theorem. So the conclusion is, if we put, the conclusion is, if we put a source of light at one of the focus, at one focus of this ellipse, then the reflected light passes through the other focus. Okay, it passes through the other focus. Okay, this is a nice property. Now we have another case, which is the hyperbola. So what happens for the hyperbola? How light is reflected on the hyperbola? Okay, now we will study this question. Now the hyperbola, suppose we have a hyperbola. Okay, suppose we have a hyperbola. Okay, suppose we have a hyperbola. Okay, so this is the asymptotes. Now we plot the hyperbola. Okay, so we have a hyperbola. Okay, now it has two foci, f2, f1. Okay, now suppose we have some external light that goes into towards the focus f2. Suppose we have a beam of light. Okay, so in the direction of so suppose it's point P. We have point P. Okay, now we started some geometric property and then conclude how light is reflected on this hyperbola. Okay, suppose we have a point P. Okay, this one note just goes wrong. Okay, maybe. Probably the file is too big. Sometimes one note can go wrong. Yeah, this one note goes wrong. Let me maybe close it. Okay, maybe let me close it. Sometimes if the section is too big, then one note sometimes can go wrong. Okay, let me close it. Restart it again. I hope it's not lost. Okay, it's still there. Good. Okay. Okay. Okay, let's start. Continue. Okay. Now we want to study how light is reflected. Now we first with some geometric property. Suppose we have one P on this hyperbola, PF2, PF1. Okay. Yeah, this file is too big. Let me start another one. This file is too big. Okay. All right. Let's start a new section. New notebook section. So we want to study how this thing is hyperbola. Okay, how light is reflected on hyperbola. So we first start with a hyperbola. So we have a hyperbola. Okay. There's two branches. So we have F1, F2, the two foci. Now we first study some geometry properties. Suppose we have point P. Conclusion, claim. So for any point P, the bisector point P on the hyperbola, then the bisector is tangent. Then the bisector of F1, P, F2 is tangent to the hyperbola at P. Okay, at P. For instance, if you choose a special point, you choose the point P to be the vertices. For instance, you choose the point P to be the Q. If you choose the point P to be the point Q, then you see the bisector is vertical. The bisector is exactly vertical. Okay, so this is a special case. It's a special case. Okay. Now, you see, if P is at infinity, what happens if P is at infinity? If P is at infinity, then if P is infinity, what happens if P at infinity? What happened to the bisector? If P goes to infinity, then the bisector will be parallel, looks like a parallel to the asymptotes. Okay, asymptotes. Okay, now we if we make this claim, assume this claim, then what we can conclude is the following. So assume this claim for now, tangent L. Tangent L. Assume this claim for now. Then what we have is the line L is bisector. So suppose we have light, a source light at infinity that in the direction of F2. So suppose we have a beam of light in the direction of F2. In the direction of F2. Now let's use S means source. Now then how light is reflected on the surface P, locally at P. Now locally at the surface P, how light is reflected, then we need to use the tangent line, okay? Tangent line L. Then you see we have alpha, we have beta, we have gamma. Suppose there exists a ray SF2 that intersect at reflected at the hyperbola at P. The hyperbola. So suppose we have a ray in the direction of SF2 intersect the hyperbola at P. Then the tangent line is the bisector. Then we have alpha equal to beta. Gamma, by the geometry condition, we have gamma equal to alpha. Okay, gamma to equal to alpha. By the construction, geometry construction. And also gamma, so this is by geometry. All they are called opposite angles. And also gamma equal to alpha. So gamma equal to R beta. So this is reflection law. So this means alpha equal to beta. So this implies alpha equal to beta. So this tells us the reflected light should pass through the point F1, i.e. So the reflected light passes through the other focus. Okay, the other focus. We don't have enough time to explain how we actually exactly that the tangent line is exactly the bisector. Okay, assume so we make this claim. We don't have enough time to show the claim. Now the idea is the same with how we showed this for the ellipse. The key thing that we use is the fact that PF1 subset PF2 is 2A. Okay, it's 2A. It's 2A. Then the idea is the same. Assume you have another intersection and show that this is impossible. Okay, shows that it's impossible by triangle inequality. So we don't have enough time for that. So it's not a bit. So you may try to work this out. We don't have time. Now the application of this is if you have this kind of surface. Okay, if you have this kind of surface. If you create a surface of hyperbola, okay, if you create this surface of hyperbola, then if you choose, you put the focus F2 in the direction of the sun, then the reflected light will focus on one point. You see the word focus, okay? This explains the name of the focus, we call it a focus. Then all the light, reflected light, will focus at exactly one point. So this kind of thing, if many light is focused on one point, this can create a higher temperature. Okay, use this, you can collect the energy to one point, F1. This has really nice application in physics, how we use solar energy using this kind of optics systems. Okay. Okay, maybe let me stop here for today, and let's continue on Monday.